Alright, so now that we have the product and the quotient rule under our belt, we'll just kind of remind ourselves what we have going. Our product rule, if I have the derivative with respect to x of f times g, we are going to remember to do gf prime plus fg prime. And if I want to do the derivative of a quotient, f over g, with respect to x, then what we're going to do is we're going to do the low d high minus your high d low all over your low squared. Okay? So however you want to remember it, make sure you have your rules. We do want to make sure that we're being effective and efficient. That we don't always, just because we see a fraction, use quotient rule. For example, here, even though I have a fraction, and you might be tempted to use quotient rule, just recognize that divided 6 is a constant. There's no need to use quotient rule. You'll get the answer eventually with quotient rule, but it is not effective nor is it efficient. What you want to do is rewrite this, simplify early and often. That is going to be your mantra when you are doing this, because it'll make your life so much easier if you think about doing it the best way. You have to remember, you only get 2 minutes for a multiple choice in the non-calculator section, 3 minutes in the calculator section, and then you only get 15 minutes for each each free response that has 4 parts to it. So you have to be fairly efficient in this and not be fooling around. So what you really need to do is go, oh, hey, wait a minute, this is really 1/6 x squared minus 1/2 x. If you recognize that, you see this is not even quotient rule at all. All I am going to do to take the derivative is do the power rule. So don't, just because you've learned a rule, that doesn't mean that you need to always use it. So I would end up with 1/3 x minus 1/2, and then we're done with the problem and we walk away. Same thing here, it looks like a fraction, but you need to recognize, wait a minute, this is really just 5/8 times x to the 4th. This is also a power rule problem. It is always quicker to just simply use the power rule in a situation like this. 4 times 5/8 would give me 5/2 x cubed, and then we're done and we walk away. So we're not going to use quotient rule in these situations. Even if I have something like this, yeah, I could use product rule, but you're going to have to distribute and simplify in the end, and this is so simple that you might as well just go, hey, that's 2x squared plus 10x, and instead of using the more difficult product rule, go ahead and simply use multiply it out first. I mean, you kind of have to make a decision. There will be sums that where you make a call and you say, well, either way it's about the same, but you basically want to work with this. So basically we just take the derivative from here, 4x plus 10, and we're done with the problem. You want to be efficient and you want to be effective, and you want to do it in the quickest way that you can. That's going to be the only way to kind of get through this AP. Right? Even if I'm looking at this one right here, you know, you could use quotient rule here, you could distribute and then use quotient rule, but this is such a simple problem, I would probably still go ahead and go, well, -3 times 3x is going to be -9x over 7x, and then distribute your -3 through there, which is going to give me a 6x squared over 7x, and rewrite this into -9/7 plus 6/7 x, and then take the derivative. That there will be times where this will be a lot quicker simply to rewrite instead of just going, oh, I have quotient rule, so now I'm going to use it every single time, because your derivative here is 6/7 and we're done. All right. Now, a couple of things, kind of using product versus quotient rule. I mean, what I hear from kids is they see this and they say, hey, I'm not going to do that. What I would prefer instead is to go ahead and use this rule. But the problem that you have here is you're actually turning a rule that you know. This one is definitely quotient rule. You have a function divided by another function. When you bring it up and you go, hey, I'm just going to use product rule, you kind of have a problem here. The fact that this is a composition, you have a function inside of a function. This is really your f of x, and then you basically have a kind of h of g of x thing going here. And we have not learned a rule for this yet. We will learn a rule, but this is more complicated. Obviously, because we haven't even learned it yet, we're kind of taking our rules in order from easiest to hardest. This rule is going to be called the chain rule. And since we haven't learned it yet, you want to be very, very careful about creating a situation that you don't have a rule for yet. So you do not have composition yet, so you are not going to rewrite this in this fashion because it's not simply a term, it's a function inside of that. So you want to be very careful. All right? So now while we're here, let's do a few more special derivative rules, kind of practicing using our quotient rule. Now obviously, what am I basically coming up with here? What is sine divided by cosine? That is our old friend tangent of x. And so the idea here is that what I can basically do, the trig functions I have derivatives for so far are sine and cosine. We haven't done a derivative of tangent yet, so maybe I'd like a derivative of tangent, and how can I come up with it? Instead of using the limit definition, now that I have quotient rule, I can rewrite this as the derivative of sine of x over cosine of x, and I now have quotient rule, and I can use the derivatives of quotient rule because I know the derivative of sine and the derivative of cosine. So we're going to do our low d high, derivative of sine is cosine, minus your high, d low, derivative of cosine is, careful, negative sine, and again, put your parentheses in because we don't want to get confused with subtraction, all over your low squared. If we simplify, the top is cosine squared x plus sine squared x, and hopefully some bells are going off in your head that we have seen the numerator before, that is nothing more than our old friend Pythagorean theorem is equal to 1. And 1 over cosine squared is secant squared of x. And so we can use the quotient rule to develop some new rules to add to our flashcards. So now we're going to have 1. We're not going to always, when we want to take the derivative of tangent, we're not going to repeat this every single time. We are going to memorize that the derivative of tangent is secant squared x. So we're going to add this to our list of derivative rules. So far today, or in this section 3.3, you've added a product rule, a quotient rule, and now we've added a derivative of the tangent. And in a similar fashion, we can basically come up with the derivatives for all the other trig functions. Here's the tangent one I just did. Here's your derivative of secant, your derivative of cotangent, and your derivative of cosecant. Okay, I'm going to leave these three for you to practice deriving on your own, okay, by rewriting it as a quotient, each one. Remember, secant is 1 over cosine of x, use your quotient rule. Cotangent is cosine x over sine x, and cosecant is 1 over sine x. So I will leave the derivations for you to practice, but you basically need to memorize these rules. The nice thing with these that make them a little easier to remember, once you get that tangent is secant squared and secant tangent, notice that cotangent is cosecant, and the only difference is when you have a C, you put a negative. Cosecant, cosecant, cotangent. They look very similar. They're not hard to memorize. But you do need to add these to our list of 4 new functions. All right, so let's do a quick practice of these derivatives. All right, g prime of x. We have the derivative of a difference, so we take the derivative of each one. Derivative of x, 1. Derivative of tangent, secant squared x. If we were simplifying, we might want to recognize that's one of our Pythagorean identities, and that is equal to negative tangent squared x. If you don't recall these are things that you kind of need to have in your tool belt. This will help in the multiple choice section. That 1 plus tangent squared of x equals secant squared x. So that's one of those trig identities that you should kind of have in your tool belt. And so kind of thinking about this, if I subtract secant squared over and subtract tangent squared over, that's how I know what to substitute in. Or you could just substitute in 1 minus parentheses 1 plus tangent squared x, and you would get there. So you kind of have to have those in. Multiple choice does not care that you don't know your trig identities. if this is your choice, you need to get from this answer to this answer in your multiple choice. This is also much nicer when you're solving as well to have it one single function. All right, over here in the second one that we're practicing, we would have our product rule. Don't get stuck when you do these if you don't realize that you actually have a product rule. Make sure you're saying that I have an f and a g here. So my dy dx, or y prime, however you want to name that, is going to be your second secant of x times the derivative of the first, which is basically 1, plus, and this is where you don't get confused now that you've got quotient rule, don't put a minus there, your first times the derivative of the second. The derivative of secant is secant x tangent x. And so if we didn't have to simplify, we would leave it there. But again, remember I said that most of the time you really like your derivative to be factored. We have a common factor in the two terms that we have going here of secant of x. So we are going to go ahead and pull that out, your GCF, and what we have left is 1 plus x tangent of x. So that would be our simplified version of this. All right, another example. Let's differentiate these and see what happens. We're going to use the quotient rule over here. Okay. Our f prime of x would be our low, b high. The derivative of cosine is negative sine times that negative would give me sine of x minus your high times the derivative of the bottom, derivative of low, sine of x derivative is cosine, all over low squared, sine squared of x. Let's do a little kind of collect like terms. We don't have anything to factor out, so let's write this as sine squared x minus, and we can go ahead and distribute here. It'll be minus cosine of x and plus cosine squared of x over sine squared x. As we are simplifying here, look, we can see that we have a sine squared and a cosine squared. I can regroup if you would like, because what we want to notice is what is sine squared plus cosine squared. That's our old friend, the Pythagorean theorem. So we end up with 1 minus cosine of x over sine of x. And we can even take it a step farther when we're looking at this. This is the same as 1 over sine of x minus cosine of x over sine of x, which is going to give me cosecant of x minus cotangent of x. So the derivative of this, and what's kind of interesting about this function especially, the derivative of this is itself. Kind of coincidental, and it actually ends up being cosecant x minus cotangent x. Now, let's use this one, and we're going to take the derivative using just our little trig rules we had above. So we have g of x, derivative of cosecant is going to be a negative because it's got a c, and then if you forget them, you come right back up here, but you'll eventually get them memorized. Derivative of cosecant is negative cosecant x cotangent x minus the derivative of cotangent was negative cosecant of x. This is going to give me negative, let's pull the negative cosecant out, cosecant of x times my cotangent of x minus 1. And of course, when you get to here, I go, wait a minute, I've made a mistake. Come back over here, and when I split these here, what did I forget? I kind of made a little boo-boo. This is a square here. So I should have a square here, so I should have a square there. So now let me fix this one so that we have what we're looking at. So this is going to be cosecant squared x, and then we're going to have minus, we could rewrite this as cosine x over sine of x times 1 over sine of x, which is going to give me cosecant squared x minus cotangent x cosecant x. And then let's come back up here, and so I don't need to do as much work as I thought I did on this one, just to prove that they are the same. Darn, pay attention, don't make any careless mistakes. When I distribute this out, this is going to end up being derivative of cotangent is negative cosecant squared. So we're going to end up with cosecant squared x minus cosecant x cotangent x, and hopefully I don't have to do anything else to show that those are the same. Now we should have known this from the beginning, since if I were to split way back up here, that this is the same as 1 over sine of x minus cosine of x over sine of x, which is g of x. So of course they have the same derivative, and so it's just different forms that we're going to be looking at. What typically is a little nicer is a lot of times this is considered a nicer derivative, because if I had to determine when it was equal to 0, I could just look at the numerator, than this one. Typically you're going to have to, if you see this one and you have to solve it, you're going to have to do some work to get it into the fraction form anyway. So a lot of times, even though we might say, hey, we don't like to use quotient rule, there will be times where we will prefer quotient rule given what I know I need to do with the derivative after this. Right, so kind of maybe what would be the reasons why I would have circumstances where I want to use the answer in a particular form. Well, really a lot of what it has to do with is depending on whether you're in your multiple choice section or whether you're in your free response section. If I'm in the multiple choice section and all of my answers are in terms of sine and cosine, then I would definitely use the quotient rule on this. I would leave it with the sine and the cosine, okay? However, if my answers that I'm looking at in my multiple choice, I'm kind of planning ahead. I look at what my answer choices are. If they have cosecants and cotangents in them, then I would like to kind of split this over and use B and use that method instead. When do I know I need to switch, and when should I leave it alone? Should I simplify first, or should I wait to the end? That's going to be your choice. If you're doing the free response section, it's kind of either or, your choice. Which one do you prefer to work with? I will say that, however, if I'm going to use the derivative, and if I am going to look for horizontal tangents, and a little bit later we're going to talk about where you might have vertical tangents, that it actually is going to be much nicer if we have the derivative in the fraction form that I have starred right there. So a lot of times we're going to prefer quotient rule, because if I have a single fraction, it makes it easier to determine when the top is 0, when the bottom is 0, and we can find those horizontal tangents and vertical tangents.